Hi, I am Dr. A.J. Kumar, PhD. This is Abstract Algebra 28. Recovering from a botched take. This is section 2.8 cosets. So I already did the thing where I went through and highlighted the backward references, and then highlighted something that was important, highlighted all the terms that I saw, and then got through like a quarter of a page, and then had to stop the video. So we're starting over. 2.8 cosets, there was a link to buy this book down below. This is going to go well with Revelations 23, which is still in draft, but once that's finished, one of the things I'm going to do in that book, or that Revelation, is iron out a lot of the group theory arguments, give a lot of examples, and we'll see. As before, if H is a subgroup of G and if A is an element of G, the subset AH for H and H. So the way I'm presenting it in Revelations 23 is you think of groups as a set of functions that act. You think of a group as acting on something, and the thing it acts on is called the stage. And what happens when you have a group act on a stage is it transforms the stage into a new space. So and typically what happens, so an example would be if take the plane, a very simple example, the plane Q2, I don't like real numbers, and divide out or have it be acted on by the Cartesian product of Z with Z, by the group of translations. Translation means move. So basically what you're doing is you're changing your, so you have the plane, and you're changing your definition of equals and saying any 2 points that are an integer coordinate apart, I'm considering to be the same point. And the resulting space you end up with is the torus. And to convince yourself of that, what you do, you can take a piece of paper, okay, and you fold it. So take a piece of paper. Okay, you can fold it so that these two edges match. Okay, and out of that you get a cylinder. Oh shit, I gotta pay my credit card bill, I forgot about that. And then you fold it again so that these two edges match. And that's how you get a torus out of the plane. So in particular, if you imagine the piece of paper was square and its size is 1 integer by 1 integer, what you're doing here is seeing the effect of taking points that are an integer coordinate apart and defining them to be the same. So this is the general way in math that you construct new spaces. You construct more complex spaces out of simpler spaces by quotienting by a group. That's typically how it works. And so here we're seeing there's kind of this circular thing, because in order to define a quotient group, you talk about the group acting on itself. So in particular, we're looking at what happens when we have G act on a subgroup of itself. Okay? And yes, so what happens when you have G act on a subgroup of itself, the resulting space are called the cosets of H. In this case, the left cosets of H. H. So the subgroup H is a particular left coset because H is 1H, right? Good. So the cosets are the parts of the stage, are equivalence classes for the congruence relation. A is congruent to B if B is equal to AH for some H and H. Okay? Cosets of H and G are equivalence classes for the congruence relation. For the congruence relation. A is congruent to B if B is AH for Right, so we're saying that two things in... oh, okay. So the cosets are the equivalence classes, for the inclusive congruence relation on G. A is congruent to B if B is equal to AH for some H and H. Okay. Transitivity. Suppose that A is congruent to B and B is congruent to C. This means that B is AH and C is BH prime for some elements H and H prime of H. Therefore, C is A times H, right, okay. Since H is itself a group, HH prime is an H, and thus A is congruent to C. Got it. Okay. Symmetry. Suppose A is congruent to B, so that B, yeah, then A is BH inverse, so. Right? Yeah, and everything is congruent to itself because because of the subgroup. Note that we have made use of all the defining properties of a subgroup here. Yeah, that's important. Closure, inverses, and identity, right? The left cosets of a subgroup H of a group G partition the group. The left cosets of a subgroup H. Yeah, just because they are equivalence classes. Right, because they are equivalence classes. And equivalence, we know from the logic we did, I assume right here, or back whenever we talked about how an equivalence relation will partition any set into equivalence relations. So if you take a subgroup, so if you, the coset relationship partitions G, it partitions G. Partitions the group G. Okay. The left cosets of a subgroup H of a group G partition the group G. Partitions the group G. It doesn't matter. And the reason is because they're equivalence classes. The cosets are equivalent. Yeah. The left cosets are the equivalence classes. And the equivalence classes partition the group. Plus eq classes partition the group. Any set. Okay. And I think it's also true that if you have a partition, you get an equivalence class. Okay. So keep in mind, yes, it was true. Keep in mind that the notation A times H defines a certain subset of G. As with any equivalence relation, several notations may define the same subset. For example, in the symmetric group with the usual presentation, I'm not going to rewrite that, the element Y generates a cyclic subgroup H is equal to brackets Y of order 2. There are 3 left cosets of H in G. H is 1Y is YH, XH. Yeah, because Y squared is equal to 1, isn't it? Something like that, I think. X, Y, H. Ah, okay. Right. Okay, so this will all get cleared up. This is one of those things where you're going to build up a bunch of complexity in your head and it's all going to cancel. Okay? So, okay. H is 1y, which is YH, XH is XXY, which is XYH, X squared H is X squared Y, which is X squared times YH. These sets do partition the group. Recapitulating. Let H be a subgroup of a group G and let A and B be elements of G. The following are equivalent. B is A times H for some H and H, or A inverse B is an element of H. Yes, those are equivalent, yes. B is an element of the left coset AH. Yes, these two are equivalent, obviously. left cosets B and AH and BH are equal. Yes, okay. Yeah, I can see how these two are equivalent. The number of left cosets of a subgroup is called the index of H and G. Okay. The index is denoted by, that's terrible notation. Thus, the index of the subgroup Y of S3 is 3, which is the number of left cosets. So the index means that if you have the group act on it, so maybe index is if you have G act on H, well, equivalently H is acting on G, but let's pretend G is acting on H. How many orbits are there? Which is the same thing as parts. Are there? But just as well, if G is acting on H, you can just as well think of that as H acting on G. Okay, thus the index of the subgroup Y of S3 is 3. When G is infinite, the index may be infinite 2. When G is infinite, the index may be infinite 2. Okay. All left, okay, and I just want to give an example, which is that if you have Z acting on NZ, or NZ acting on Z, I think either way you think about it is fine. The index of Z and NZ, let me rewrite that, Z, the index of NZ in Z, this is going to be N. Okay. Because if you have 12Z act on Z, you get 12 orbits, that's clock arithmetic, or 2Z act on Z, you partition Z into even and odd. Okay. When G is infinite, the index may be infinite 2. Okay. All left cosets AH of a subgroup H of a group G have the same order. All left cosets. That's interesting. That's interesting. I'm going to highlight this in pink because this seems really important. I need to switch to the highlighter tool and then pink. Here we go. Okay. The proof is one line, so okay, I can't think of how to prove this right away, but let's just think. Let's think. All left cosets of a group G have the same order. Okay, let's just look at the proof. Multiplication by A defines a map H in standard H, this is a set, to AH, which is a set, which sends H to A times H. The map is bijective. Okay. So equivalently, all orbits are the same size in our are the same size. This is really important. Okay. Since the cosets all have the same order, and since they partition the group, we obtain the important counting formula. The order of G is the order of H so all of the orbits are the same size. The set of the orbits, the distinct orbits, form a partition of the group, form a partition. So if we imagine, let's just pretend we have a circle. Okay, let's visualize this by, in black, let's write out the clock, or I guess in green. This is what we're doing. You'll see what I'm doing in a second. Here, let me do this in my paint, so I have more room. Okay. Here we are. Okay, and let's just make a clock. Okay. And what I'm going to do is just mark the hands. I'm just going to roughly mark where the hours on the clock, and then we're going to see what this is in maybe a little bit more of a concrete context. So let me do these. Let me just eyeball. There's 10 and 11. 1 and 2. 1 and 2. So we see that we know that clock arithmetic with addition has a group structure. Okay. So what we're going to do. So we have let's say the clock Z mod 12Z. This is G, let's say, and let's try to factor out by Z mod 3Z. So we're going to need 3 colors. Let's just stick with our standard palette: yellow, green, and pink. Okay, and so we're going to color these. Yeah, okay. Ooh, whoa. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. And then, so our orbit, or our action, partitions our stage. Our stage is the clock. And then we're acting on it using the Z mod 3Z. So, ooh, what happened? I don't know. But I want to emphasize Z. This is H. Okay. Go with pink. And this defines a coloring on the original stage. So the group defines, in a sense, a coloring on the original stage. And we notice that so the colors are the cosets. So let me write this out. Colors are cosets. This is our stage, and these are our actors. Not in the like Erlang sense of actors, but more in the analogy. Okay, and our actors partition the state. Our actors color the stage like this. Okay, No, our actors are, my apologies, our actors are 3z mod 12z. That's my apology. That's my mistake. Our actors are 3z divided by 12z. Okay? Right, and then so we have this thing where we do z mod 12z divided by 3z over 12z, and somehow we end up with z over 3z. That's why this quotient notation kind of makes sense. 3z over 12z is our actors, and so we take our stage and divide out by our actors. They're the same. There are four pink dots. I just want to emphasize 4 pink dots. Four yellow dots and 4 blue dots. 4 blue dots. Same number. Okay. The index so the index of let's just use the IDX of 3z over 12z in and it's the index. The index of 3z over 12z in z over 12z. Yeah, and so if you take 2 plus 3, so 1 plus 2, that's 3. Yeah, and then this is a new group, because if you take a pink and add it to a blue, you get a yellow. So if I take, let's say, 2 and add it to, this is 7, I'm going to get 9, which is a yellow. Yeah, so pink plus blue is equal to yellow. Let me just write this out. Plus is equal to yellow pink plus blue is equal to yellow. So, right, and so let's just do, let's look at the counting formula. Maybe I should put these notes up on my have the notes go somewhere. the counting formula. Yeah, I need to start putting the notes up. So I think what I will do is when I get OPHTTPD up, is every video I will put a link to the video. All the links to the video will go up. Any additional notes, any additional files, something like that. I don't know. I'll have to see. Okay, counting formula. But let's say the order of Z12. Okay. Is equal to the order of 3Z over 12Z. The order of 3Z divided by 12Z. The order of 3Z divided by 12Z times the so this is 12. Okay. This is equal to 3, which is the num. So the index is equal to the number of orbits. And then the number of orbits times the size of orbits. 4 is equal to size of each orbit. Each orbit has the same size. Okay, so to 4 times times 3, which is the index of 3Z over 12Z, subgroup of 12Z. So size of stage is equal to size of orbit times the number of orbits. Well, kind of fucking duh once you see it like this. Okay, I'm going to save this as AA28. Okay. And I want to export it as a PNG. Okay. And what I want to do is see if I can import a PNG into here and make it like really small. Page. Is there a way to import a PDF or import a PNG file? I don't see. And then is there a way to export this? Huh. Anyway. There's no way to export this as a PDF, is there? Anyway. Oops. Okay. Anyway. That's interesting. Okay, so let's... This counting formula. Counting formula is, just to repeat, the size of the stage is equal to the size of each orbit times the number of orbits. And the size of each orbit is constant. That's this idea. Is constant. And this is the number of orbits is the index. So size of stage is this term, size of each orbit is this term, and the number of orbits is this index. Okay. Yeah. So size of stage is the order of G. The order of H is the size of each orbit, and the number of cosets is the number of orbits. Okay. Okay. Whereas always, order of G denotes the order of the group. This equality has the obvious meaning if some terms are infinite. For the subgroup Y of S3, this formula has the obvious meaning. Okay, so it's infinity is infinity times something like that. Okay, yeah. For the subgroup Y of S3, the formula reads 6 is 2 times 3. Okay, we'll have to. We're gonna work out a lot of examples with S3 because S3 I think is the simplest. Yeah, right. So to do. This will be in Rev 23. Is work out a lot of examples with S3 because it's the simplest, not a lot of examples with S3. Because I think S3 is the simplest non-commutative subgroup. And so that's why he keeps going to it. Because he's referenced S3 multiple times in every single section. Okay. Anyway, right, it follows that the number of orbits is the size of the stage divided by the size of each orbit, right? Okay, right. So the order of, right. And then the corollary of that, because you can do this with any subgroup, is the order of any subgroup divides the order of the group. Okay, proof. The order of an element A of a group G is equal to the order of the cyclic subgroup A, brackets A, generated by A. Order of an element A of a group G okay, the order of an element of a group (242). That is page 46. Let me look at that, because now I'm lost again. The order of an element of a group is equal to the order of the cyclic subgroup that it generates. Okay, this doesn't seem complicated. I'm just having a brain fart. Okay. Order of an element of a finite group. Okay, so you take a group and you basically trace the you trace what happens. You pick an element and you take its cyclic group. Okay. The order of an element A is equal to the order. Okay. Right, and that has to divide the order of the group just because it's a subgroup. Okay, yeah, okay, just because of Lagrange's theorem. A is a subgroup of G, and Lagrange's theorem. Okay. Suppose that a group G has prime order P. Right. Corollary, suppose that a group has prime order. Let A be any element of G other than the identity. Then G is the cyclic group A generated by A. Right, so every element of a prime ordered group is a generator just because P has no divisors. And so the order of it, yeah. Yeah, other than the identity, that's important. Okay. I need a bigger. There we are. Okay. Whoa, we've still got, just gotta look, 58. Oh my god, we have like a page and a half left. Okay. This corollary classifies groups of prime order P. They form one isomorphism class, the class of the cyclic groups of order P. This corollary classifies groups of prime order P. They form one isomorphism class. I'm going to put a next to this. Because I'm a little bit not 100% on that. Okay. The counting formula, I don't see why it's wrong, but it's also, they form one isomorphism class. I'm really kind of hung up on what exactly this means. So they are all isomorphic to each other. I can kind of see that, all isomorphic to each other. To each other. Yeah. The counting formula can also be applied when a homomorphism is given. As we have seen, the left cosets of the kernel are the non-empty fibers of the map. They are in bijective correspondence with the elements of the image. Counting formula can also be applied when a homomorphism is given. Let's think about this. The counting formula can also be applied when a homomorphism is given. I know all the words and it's just the sentence isn't working. It's just one of those days that it seems like. God damn it. Okay. G. Okay, I understand. Okay. If I read a whole paragraph at a time, it makes sense. So the count here, let me blow it up so you can read it. Sorry. Okay. Equals. There we go. The counting formula can also be applied when homomorphism is given. So, right, we saw this, that if you have right, so if you have a homomorphism, right, so this is the typical diagram. You have G, you have can't remember exactly how the diagram goes. You have phi to some other group, gamma, let's say. Okay, and then you can go also to G mod cur phi down like this. This is another homomorphism, and then these two groups are isomorphic. There's a quote canonical isomorphism between those two groups. That's the this is usually called the fundamental theorem of homomorphisms. I'll just do fundamental theorem of homomorphisms. And so this is kind of the shadow of the fundamental theorem of homomorphisms. The left cosets of a kernel of phi are the non-empty fibers of the map phi. They are in bijective correspondence with the elements of the image. So G cur phi is equal to M phi. Okay. G cur phi is M phi. Okay. The counting formula can also be applied when a homomorphism is given. As we have seen, the left are the non-empty fibers of the map. They're in bijective correspondence. That's really important. Bijective correspondence with the elements of the image. So therefore, right, the index of G and cur phi is the m. Right, and this is the order of G mod the order of the kernel phi, because the kernel is obviously a subgroup. This is equal to the M phi, and what you can do the quotienting as long as the subgroup is a normal subgroup. Normal subgroup is equivalent to it being the kernel of a homomorphism, which is, this is in a sense the order version of this theorem. These two are kind of birds of the same feather. Okay? So let G to G prime be a homomorphism of finite groups. Then order of G is kernel of phi times image of phi. Right. Right, I just wrote this up here. Then kernel of phi divides G, right, and image of phi divides both. Okay, well the image of a homomorphism is going to be a group. Just because you can pull it back. You can pull back the group structure. So the image, yeah. And so, because it's a group. I don't even need to read the proof, but let's just scan the proof very quickly. Yeah, since the image is a subgroup. Oops, what I just wrote. Since the image is a subgroup. The smartest mathematician who ever lived. Anyway, the sign homomorphism. Okay, the sign of a permutation. Okay. Sign homomorphism of a permutation. Okay. It is surjective, so its image has order 2. Its kernel has order n half of n factorial. Right, okay. Because the order of Sn is n factorial, and this is equal to the order of the kernel of that map, which is an, times the order of 1, 2, so therefore, or of 1 minus 1. And so therefore, the order of an is n factorial divided by 2. Right, okay. So half are even and the other half are odd. The counting formula has an analog when a chain of subgroups is given. Oh boy. May have to take a break because my brain is on fire. Okay, we have another page. Jesus Christ. Oh. Oof. Okay. I have earned something after this. Anyway, let GHK be chain of subgroups of a group. Then GK it's GH, HK. So, yeah, let's just assume finite for now. Okay, I'm not going to worry about infinite. Okay. So yeah, if one of these is infinite, then it kind of blows up the whole thing, but then you don't really get a contradiction, so it's fine. We list the m cosets of H and G. Okay, G in H is M, and H in K is N. Okay. The m cosets of H in G. The m cosets of H in G then partition of G, then we can partition H, okay, I gotta zoom out so that I can kind of scan the whole proof. This is too big for me to read. Okay, G and H is M, and G, okay. So here are the cosets, so the orbits of H, okay, as given by certain elements in the group, in G. The orbits of H as given by the elements of a group, or as given by canonical representative elements of G. Okay? And since the orbits partition the group, G up to GMH is a partition of G. Okay. Ah, okay, this makes sense, right. So, maybe if we could draw it as a tree, it'll make sense. So G partition into, where do I have room? Let me zoom in really far and draw it really small. Okay. So think of it as a tree. So we take G, partition it into orbit of H, partition G, G into M orbits of H, and then this is step 1 in this proof. Partition G into M orbits of H, partition this, partition H to partition H, H into N orbits of K, so, and then just kind of delete this second level, and you now have a partition of G okay, so it assumes this is given, and this is given, and proves that their product is equal, prove product to I dx k g. So an example of such a chain would be Z, 3Z, and then let's say 12Z. Right? Yeah, and now we've partitioned G into, and then putting these partitions together, yeah, this is step 3. Okay, right cosets. Okay, let's go back to the definition of cosets. We made the decision to work with left cosets. We can also do the right cosets. Okay, the right cosets are equivalence classes, blah, blah, blah. Because the logic, there was nothing specific to leftism in the upper logic. Okay. They're equivalence classes for the relation A is equal to B if B is equal to HA for some H and H. The right cosets also partition the group G, but aren't always the same as left cosets. For instance, the right cosets of a subgroup Y of S3 are H is 1Y is HY, HX is equal to X, X squared Y, which is, okay. Are these cosets are not the same as before, are they? They are not. Okay. Yeah, this isn't the same as the partition in the left cosets, right. However, if a subgroup is normal, its left and right cosets are equal. Okay, proposition. This is going to be a really important proposition. You can already tell. So let's put a big star next to it for important. Important. Let H be a subgroup of a group G. The following conditions are equivalent. H is a normal subgroup. Yeah, I've changed my mind. Artin is definitely, this is the Rudin thing where he's making my brain eat itself. Okay. And this isn't even like unfamiliar. We haven't even gotten to the parts that I don't know yet. This is stuff that is review for me, and I'm just, my brain is not handling it. I think it's because I was drinking some of that fluoride water. Okay, let H be a subgroup of a group G. The following conditions are equivalent. H is a normal subgroup of G for all H and all G and G, GH, inverses an H. Okay, but it's not necessarily equal to H. If it is equal to H, then H is part of the center of G, but yeah. So centrality, okay, normality, or centrality implies normality, but normality does not imply centrality. Okay. For all G and G, GH inverse is equal to H. So this is a set, and this is a set. This is set equivalence. This is a set, and this is a set. CIA notation, but we'll deal with it. For all G and G, the left coset is equal to the right coset. Okay. Sure. Every left coset of H is a right coset. Okay. Yeah. Suppose that H is normal, so that I holds. So let's just work out the basic logic of how he's proving this. So he's showing 1 implies 2, showing that 2 implies 1, 2 implies 3, 3 implies 2, 3 implies 4, and then 4. Okay, so he's just showing the up and down implications. Okay, sometimes you'll show a chain of implications. That's always fun. Okay, suppose that H is normal. So I holds. suppose that H is normal, so I holds. Right, so, right, this would mean that the G, okay, I'm just going to write it in set notation, GHG inverse, each of these is in H, for all G in G, H in H, no, fixed, is it, no, sorry, for fixed G in G, fixed G. GHG inverse in H for all H in H. This is a subset of H, certainly. Okay. Yes, so we're at this part, I agree. Substituting G inverse for G. I don't think you can multiply that. Why can you multiply this inclusion? I'm a little bit iffy on this step, and I'm kind of constrained for time. Huh? This is a glowy move by Artin, is to use some ridiculous notation and then say that you can multiply using it. Okay, so this is a glowy move. So we're highlighting it in glowy green. It's a glowy move. Okay. 2 implies, yeah, okay, sure. Next, if, so we're going to have to come back and work on this, huh? Therefore, this shows that 1 implies 2. So let me make a list of things I want to iron out in Revelations 23. XB, things I want to iron out in Rev 23. Okay, and this is from 2.8. Lots of examples with S3. Before we had that 2.8, how about this? That homomorphism from S4 to S3. 2.8, lots of examples with S3. The 2.8, what page is this? This is page, this is page 59. Proof of 0.8.17. The multiply inclusion, or the conjugation of inclusions. Glowy move. Let's see, what else did I want to iron out? We'll think about it. Okay. Okay, so this is another glowy move. This weird multiplying sets thing. Here. I want the ruler back. Here's another glowy thing. Three implies 2. GH equals HG. Since 3 implies 4 is obvious, it remains only to check that 4 implies 3. Ah! So it's a right coset and it's specifically this one. Okay. Under what circumstances can a left coset be equal to a right coset? So we saw that the right cosets partition the group, and we have that the left coset and the right coset have an element in common. So if the left coset is equal to any right coset, that coset must be Hg. Okay. The left coset GH and the right coset HG have an element in common. Oh. Right. So every left coset of H and G is a right coset. Ah! Okay. So we have two partitions of the group. Okay? Here's the argument. Okay, the argument is that basically, so we have our stage. I understand this argument. This makes sense. Okay. We have our stage, and we've partitioned it in two ways. Okay? So let me just draw the stage as a circle, okay? And we've partitioned our circle in two ways, let's say. Okay. What we're saying, okay, we have two different partitions. Not parts, two different partitions. I'm just going to explain this verbally and then try to come up with an image later, maybe. We have two completely different, we have two different partitions of the group. Okay? What we're saying is that, hey, what we can show is that, so we've partitioned using method A and partitioned using method B. Okay, we don't know if they're the same, if the partitions overlap. But what we can show, let's assume that we have shown that one of the parts in method A, or the left method, the leftist method, and one of the parts in the rightist method match. Okay? We can show, first of all, that they must have an element in common. Right. So we want to figure out, okay, we know that it's GH from the left. We know that it's going to have an element in common with HG. Okay, and the nature of partitions is once you show that you have one element in common, you have all the elements in common. So if we know that one of the left parts matches one of the right parts, and we know which left part it is, we also know which right part it is, and so therefore 4 implies 3. That's the logic here. Okay, I'm going to have to iron that out a bit. Okay, iron out. Jesus Christ. Iron out. Iron out. Iron out. Okay. H is a subgroup of G, and G is an element of G, then set GHG inverse is also a subgroup. And if it is equal to H, what is this? Spam. These Indian scammers are making honest Indians like me look bad. Anyway. Conjugation by G. Okay. H is a subgroup of G, and G is an element of G. Then GHG inverse is also a subgroup. So it's an automorphism because it's a homomorphism, and it's invertible. Okay, sure. Okay. So it's going to map. So homomorphisms map groups to groups. So it's going to map H to some other group, some other subgroup of G. Okay. This conjugation will map, because it maps groups to groups, it will map I gotta look at 264, that's page 52. Okay. Okay, yes, so this is an automorphism because, first of all, go look at page 52 in your book. This is an automorphism because, first of all, it is a homomorphism. This is an automorphism. Okay, let me reset for like 30 seconds and then think about this. Okay. This isn't hard. My brain is out of gas. If H is a subgroup of G and G is an element of, okay. So it's a map. So let's just think of it as a group homomorphism from H to G. And the image of this, because since H is a subgroup of G, it's obviously defined. So it's a homomorphism. So its image will be a subgroup of G. Its image of this will be a subgroup of G. G. Okay. Okay. Let's think. Its image will also be a subgroup of G. Image will be a subgroup of G. It's just my brain is not thinking 2 steps ahead. It's thinking 0 steps ahead. Okay. GHU, yeah, okay, yes, okay, let's just agree that, yeah, that makes sense because it's the image of a homomorphism. Image of a homomorphism. Homomorphism. Yes, and that's his logic, okay. If a group has just one subgroup of H of order R, then it will get mapped to a subgroup of equal or smaller order, but equal because it's because there's only one subgroup, so there's only one choice. Choice of where it goes. Okay, that makes sense. If H is a subgroup of a finite group G, then the counting formulas using right cosets or left cosets are the same, so the number of left cosets is equal to the number of right cosets. This is also true when G is infinite, though the proof can't be made by counting. See exercise M.8. Okay. I do want to look at exercise M8. I'm going to look at that in my book. What does this exercise say? Is path connected? What the fuck? This is interesting. I want to look at these groups, actually. I want to look at these miscellaneous problems. This looks really interesting. Okay. Maybe what I will do is a series that is going to be locals exclusive, because I don't want to do... Okay, I think this is something I'm going to do. I'm going to do a locals exclusive a locals exclusive thing where I just work through some problems from various textbooks. And the reason is that if you need to cheat, if you need to cheat, then you're gonna have to pay me for it. If you're cheating on your homework, you have to pay me. Okay, that's the rule. Okay. Okay. These look really interesting. So you know what? I can show you the problems. I'm not going to walk through how to solve them, because it starts with. Okay, let's look. Exercise. So page 75. God damn it. Page 75. Where are we? And I will pick some problems that I think are interesting. 75. Okay. These are interesting. So let A equals A1 up to AK and B equals B1 up to BK be points in k-dimensional space RK. A path from A to B is a continuous function, right, I know what a path is. Okay, path connectedness. Okay. Yeah, path components. You need some more topology, because there's like a set that's there's a set that's connected but not path connected. There's bullshit like that. this is a little bit. There's some CIA stuff going on here, so let's put this in the glowy color. So there's some CIA stuff going on here with some topology. Okay. The n by n matrices can be identified with the space Rn to the n times n. Let G be a subgroup of GLN. With the notation of exercise m.6, prove if A, B, C, D are in G, loci means fiber. This is yes, maybe, I'm not sure, and this is definitely a no. This is a yes, and this is a no. This is a hyperbola, so this is y equals 1 over x, which, so it's definitely not path connected. There's two branches of it. Let G be a subgroup of GLN. With the notation of exercise m.6, prove oh, this is like the very basics of Lie group theory, isn't it? Okay. They're connected. Do you mean the connected component of I? Okay. Use this fact to prove that SLN of R is path connected. Son of a bitch. Okay. I am definitely going to look at this, but this will be a, because I'm solving problems from a book, that'll be a locals exclusive, I think. Okay? And I don't know when I'll get to this. Okay. Anyway, that's, I might have to reread this, but I'll probably do that on my own time. Anyway, thank you for watching. I will see you in the next video. Boy, I hope I had the right numbers. Yeah, I did. Alright. I'll see you in the next video. Goodbye.